In the second part for chapter 4, we are going to focus on reactions now. There are 3 types of reactions we will do. So let me go ahead and introduce you again to different kinds of reactions. This is something that you have learned before, and that's that there are 4 kinds of reactions: synthesis, double displacement, single displacement, and decomposition. So when you learn about these 4 different classes of reactions, the way I see them is that the atoms are rearranged in all of these, right? So in synthesis, the 2 starting materials will combine to give you 1. In decomposition, it's the opposite. 1 substance gives you 2. Now, atoms are rearranged in all the reaction. There is no doubt about that, okay? So that's nothing new. It's just that when you classify the reactions, you classify them as synthesis or double displacement, right? So it's more of a physical thing that you're classifying with. Excuse me. So it's a physical thing, all right, that you're looking at. Now what we want to do is we want to classify according to chemical type. So in the chemical type of reaction, you're looking at 3 different kinds of reactions: precipitation reaction, neutralization reactions, and redox reactions, which are oxidation reduction reactions. In the precipitation reaction, a solid is formed, okay? When you look at all these reactions, by the way, remember everything is happening in water because we're doing aqueous reactions, okay? So don't forget that everything is in water. So precipitation, you're not starting with the solid. Precipitate means solid formation. So you're not starting with the solid, you're starting with solutions, and then in the end you end up getting a solid as a result. So that's a precipitation reaction. Neutralization reaction is between an acid and a base. So we'll talk about acids and bases again in this chapter. And then finally there is the oxidation reduction reactions, which is a little bit of a different kind of reaction. So we'll go through each of these and then see how they differ and how they work, okay, and how you classify them. So precipitation reaction is a formation of a solid, okay, which means that you're mixing 2 solutions together. Now remember what kind of a solution? Homogeneous solutions that you mix together. Aqueous solution, everything is in water. So when you mix these 2 solutions together, then you form a precipitate. Again, precipitate is a solid. What kind of a solid will you form? Now that solid can look like a cloudy thing. That solid could be a thick, chunky precipitate, you know, like just kind of sitting down there in the test tube. So it can be different kinds, okay, of solids that you get. So that's a precipitation reaction. So now how do you predict that? Okay, we're going to go over that. But I want to also tell you that precipitation reactions are double displacement reactions because we're going to write the reactions, and then we are going to learn the solubility rules, because really this is how you predict whether a precipitate is going to form or not. Otherwise, how do you know, right? So here are your solubility rules. Now listen carefully for these ones because I'm going to explain to you how to read this table. All right, I've tried to write it in a very simple way so you can you know, kind of understand this. So group 1 salts. Group 1 salt. First of all, what is a salt? Salt is anything that is a positive and a negative together. Okay, so something as simple as sodium chloride. All right, now you're not going to classify the acids and bases as salt, even though they have a positive and negative. Okay, but anything other than acid and bases is considered to be a salt. So what is group 1? Group 1 is the alkali metals. And alkali metals, you have the sodium, lithium, potassium, all of these. Those are all going to be soluble. So if you see here, I've written here for you that there's no exceptions here, which means that you can take any group 1 salt and it will be completely soluble in water. What does that mean? You can take lithium chloride, sodium nitrate, potassium phosphate, anything, any combination you want to take for group 1, it's always soluble. Same thing with ammonium salts. Okay, what is ammonium again? NH4 plus. So you take any of the ammonium salts and everything is going to be soluble, okay, in there. Now group 1 means what? Group 1 actually means a cation, right? So group 1 is like Na plus or lithium plus, right? It's an ion. Remember, we're always talking about ions here. We're not talking about sodium or lithium as in a metal. So these are all ions. So whether it's, NaCl or Na3PO4, whatever phosphate, whatever salt it is, it's fine. But these are cations coming from group 1. Ammonium salt is also a cation, right? NH4 plus. Nitrates, acetates, perchlorates, these are polyatomic ions. The polyatomic ions, nitrate, and you can write this on your own, NO3 minus, acetate, okay, I'll write acetate. Well, then in that case, I'll write nitrate also. So NO3 minus is nitrate, and acetate, the way I write it, is CH3COO minus. That's an acetate. And acetate is coming from acetic acid, okay? Just like nitrates form nitric acid, right? And all that. But we are talking about salts, which means what? So nitrate could be anything. It could be calcium nitrate, okay? It could be lithium nitrate, any nitrate, it doesn't matter, and not HNO3. HNO3 is nitric acid, so that is an acid. But any nitrate, you can take iron 2 nitrate or aluminum nitrate. All nitrates are soluble. Similarly, all acetates are soluble. Now perchlorate we have not really kind of talked about, as in polyatomic ions. I did not ask you to memorize perchlorate ions, but perchlorate is ClO4 minus. But perchlorates are also all soluble. Okay, so which means all of these ions, the group 1 ammonium nitrates and acetates, these salts are always going to be soluble. If you see them in combination with anything, it's going to be soluble. No exceptions, okay, whatsoever. So now, what are the things with exceptions? Or let's look at what other things I have written here. Let me erase this in case I need some space to write some more. So then let's look at the halides. Okay, halides are what? Halides are group number 7. Okay, so whether it's fluoride, chloride, bromide, iodide, any of those. Halides are all soluble except lead, silver, and mercury. So lead chloride, for example, is insoluble. Silver chloride is insoluble, or silver bromide, silver iodide. Any of those combinations going to be insoluble. Same thing with sulfate. Okay, so sulfate, all are soluble except. So again, you have the lead, mercury, and silver, but you also have some of the group 2 now, okay, which is strontium, barium, and calcium. These are not soluble, okay, and what are they not soluble in? Water, which means what? If you have strontium sulfate, it is not soluble. Barium sulfate, not soluble. Sodium sulfate, yes, soluble, okay. All right, that's how it goes. Now we go to the other side, which means carbonates are generally all insoluble except group 2 salts. Okay, so carbonates, everything is soluble. Remember, everything is soluble except group 2 salts. What is group 2? Magnesium, calcium, strontium, barium. So barium carbonate, not soluble. Okay, calcium carbonate, not soluble. But all other carbonates are soluble. Aluminum carbonate is soluble. Potassium carbonate is soluble. Okay, all of those are soluble. Phosphates are all insoluble. Okay, now when we say that phosphates are all insoluble, what does that mean? It means that phosphates are all insoluble except where you have no exceptions. Because group 1 and ammonium salts, which are the positive ones that can combine with phosphates, these are always soluble. They have no exceptions whatsoever. So phosphates are generally going to be insoluble except for group 1 and ammonium salts. Now, if you want to write it, you can write that. I didn't write it because here they have no exceptions to begin with. Okay, so I didn't want to write it. So if you want to in your table, you can write that. Okay, so you'll remember. But otherwise, all phosphates are insoluble regardless of where they are. Okay, except for group 1 and ammonium salts. Hydroxides are all insoluble except for calcium and barium, which are soluble. Okay, so hydroxide, if I say iron hydroxide, magnesium hydroxides, all insoluble. Except, again, don't forget, group 1, ammonium salts, always going to be soluble because they don't have any exceptions. I like to remember it this way because that way I don't have to tax my brain that much. Okay, so I will always remember that group 1 is soluble. So no matter where I see lithium, sodium, whatever, I will just close my eyes and like this is soluble. Okay, so it's nice to remember some things with no exceptions, because exceptions are a little bit harder to remember. Okay, so sometimes it's easier to just remember the something that is without any exception. So group 1, ammonium nitrates, acetates, I probably will not give you any perchlorates, but the first 4, you know, all soluble all the time. So sulfides, again, not soluble except for group 2 salts. So you can see that group 2 is showing up a lot, right? So group 2 is soluble, group 2 is soluble, group 2 here is not soluble. So you can see that, you know, wherever there is a group 2, you kind of have to think, is it soluble, is it not soluble? All right, but all the others, they're only going to be soluble or insoluble. The same thing goes for lead, silver, and mercury. Okay, these are called heavy metals, and heavy metals are generally not soluble, okay, in water. They will precipitate out, okay, with a lot of things. So you kind of, you know, learn to remember these things slowly as you keep writing more and more equations, okay. But this is how you're going to read your solubility guideline, and anything that I give you generally should be within this guideline. Okay, so let's go ahead and write or predict precipitation. Okay, so all you have to do is look at these compounds and predict if they're going to be soluble or insoluble in water, and then predict the precipitate that's going to form for this equation. So let's look at the first one: barium nitrate, silver iodide, and magnesium hydroxide. So barium nitrate, as soon as I see nitrate, I'm like, I'm done. Okay, this is it. This is soluble. Silver iodide. Silver is generally going to be insoluble in a lot of things, and then if you look at your solubility table, halides are not soluble for silver, and then hydroxides are also not soluble. Remember, group 2 is a little bit different because group 2 is also called the alkaline earth metal. The earth metals are generally insoluble because they form the earth. Now, if everything was soluble in water, then we don't have any solids at all. Okay, then everything is water, okay, or everything is in water. So things are insoluble for sure. Okay, so that's why we have to kind of know all these solubility rules. Okay, now let's look at this equation over here and predict the solubility. So lead nitrate and sodium iodide. Okay, so I told you already that when we write precipitation equations, it's going to be a double displacement. Okay, so what does the double displacement mean for us? Is that lead is going to go with the iodide and nitrate is going to go with sodium. Okay, so those are the compounds that we make. Now you have to make them in proper ratio though. Okay, so lead iodide is not PBI. PBI would be the Palm Beach Airport, right? But anyhow, okay, so PBI2 is the right formula. Okay, similarly for NaNO3, sodium nitrate, it's a 1-to-1 ratio. So here if you see two nitrates, you got to balance the equation out. Okay, so that's a different thing, but you have to have the right formulas. That's what I'm telling you. Okay, so don't write PBI, it's PBI2, okay, for the formula for lead iodide. Anyway, so once you do the crisscross and you figure out, okay, the double displacement that I got, sodium nitrate and lead iodide, well, sodium is completely soluble all the time. Group 1 nitrates also all soluble, but lead iodide is not soluble. Okay, so this is going to be the precipitate. Now, again, I have some videos on precipitation reactions, so I encourage you to see those videos, and you will see how we see these precipitates. Okay, so you take a solution of this in a test tube, you take a solution of this in a test tube. So when you mix those two solutions together, then the ions will start interacting with each other. Okay, once they start interacting, then lead and iodide will get together like, we're not soluble, we are going to go hang out on our own, and so they precipitate out, okay, because they're not soluble in water anymore. Okay, so now talking about equation writing. This is a very critical part in this chapter, and I really want you to, if not master it, then get good at it, okay? Because writing equation, again, is one of those hearts of chemistry that I really believe in, okay? So I already showed you how to write dissociation equations. So when you take any kind of a compound and you dissociate it, you get ions, right? The cation and the anion. And I showed you how to take the subscript and write that as the coefficient. So that's something we have to do. The other thing we also have to make sure that we write is our states, the solid, liquid, gas, and aqueous. Okay, we have to write that. So you know, in precipitation reactions, we are forming a solid, but everything else should be aqueous. Okay, so that kind of thing you have to follow through. Okay, and I know it takes a little time, I know it. Okay, so I write these equations and I know that these things take time, but you have to take the time, okay, in order to do this. Okay, so here we are now looking at an equation. So we're going to write three equations. Okay, when we write any kind of equation, we write a molecular equation, an ionic equation, and then a net ionic equation. So there are three kinds of equations that we write. So the molecular equation is the normal equation that we are used to writing. So with like silver nitrate and sodium chloride, so you get double displacement, right? So silver goes with chlorine and then nitrate goes with sodium, and then you get silver chloride and sodium nitrate. Now, all of these you have to write in the correct formulas. If you don't, again, you can't balance your equation, okay? All right, at this point, you have to balance the equation. In the molecular equation, and I'm going to add that over here, you have to balance the equation right here. If you don't balance it here, you're going to have trouble later on, okay? I mean, it's not like a big trouble, but you should balance the equation here. Ionic equation is where everything is ionized, okay? In the molecular equation, let me just come back for a second here. In the molecular equation, you're going to figure out what is aqueous, and what is a solid, if there was any, okay? And since we are working with precipitation equations, you are working with solids. So you're going to determine if there is a solid in there or not, and you're going to write that as solid. Remember, solid is not dissolved in water. And it's not dissolved in water because it is not soluble in water, okay? And then here is sodium nitrate, which is aqueous. So when you write the ionic equation, in that ionic equation, you're going to have to just dissociate everything that is aqueous. What is not aqueous is left as is on the left and the right of the equation, okay? So silver nitrate is going to dissociate because when it is in aqueous solution, it is dissociated. Sodium chloride in aqueous is dissociated. Silver chloride is a solid. It is not dissociated. Okay, so it's just a solid. And then sodium and nitrate, these are dissociated because they are soluble in water. So this is why the dissociation writing was really important for us. Okay, so you kind of learn how to dissociate ions. So this is your ionic equation. You're showing all the ions in here, and whatever is not ionic, you show that also. In the net ionic equation, what you do is you remove what is called the spectator ions. What are the spectator ions? These are the ions on both sides of the equation. So you look on the left side and the right side. I would look more on the right side, okay, because the right side is the product side. So I always start with the right side and I see, okay, I have sodium. Do I have sodium ions on the left side? Yes, I have sodium ions. So that's a spectator ion. Nitrate ion I have on the right side. Do I have that on the left? Yes, I do. So those are gone then. So everything that is red here, that's gone, okay, in the net ionic equation, because these are called spectator ions. What are spectator ions? They're just hanging around. They got nothing to do because they're all soluble in water. Okay, so just like, you know, when you go to watch a game, you're not playing the game, you're a spectator, okay, in there. So these are just spectators. They're just watching things happen. So the final net ionic equation is really where the action is happening, and that is between silver and chloride, which is forming a solid. Okay, so this is how you write equations. All right, so now writing a precipitation equation. Decide whether the following reaction occurs, and if it does, write those equations. Okay, so we will always be writing molecular, ionic, and net ionic equations. Not always, you know, in an exam things might be a little bit different, but still, okay, you still need to practice these equations. So first of all, you need to go ahead and determine what kind of products you're going to form. Okay, now you don't have to do this if you don't want to. The step 1 and step 2, you don't have to. Okay, you can just go ahead and write the molecular equation. All right, so NaOH and magnesium chloride. So sodium hydroxide, magnesium chloride, you write the equation out and then you write the products. Again, how do you write the products? The products again are written as double displacement, right? So sodium goes with chlorine, and then the hydroxide goes with magnesium. So that's how you do the double displacement. Now always remember, when you do the double displacement, always write the cation first. Okay, so sodium hydroxide and not hydroxide sodium. Okay, so that's not correct. Always write the positive first and then the negative, and that's how it's going to be for magnesium hydroxide. For magnesium hydroxide, remember the ions. Okay, so magnesium is Mg2 plus and hydroxide is -1. So do the crisscross and you know that this is going to be the formula. Okay, so make sure your formulas are correct and then make sure that you write the positive first. Okay, when you do these kind of equations. All right, so this is the molecular equation. Now in this molecular equation, what you also have to do is balance the equation. All right, so since magnesium was needing 2 hydroxides, you need to have 2 hydroxides here. And because there was magnesium had 2 chlorides over here, you need to put 2 in front of sodium and then you balance the equation. Okay. Now for the ionic equation. So the ionic equation is Na, where you're dissociating Na. Now remember, the 2 is the coefficient here. So the 2 goes for Na. It also goes for hydroxide. Okay, so the 2 is for both. Like you have 2 molecules of NaOH. Okay, so which means that 2 of Na and 2 of hydroxide. For magnesium chloride, you have 1 magnesium, but you have 2 chlorides. Again, remember, don't make a mess. Okay, don't write Cl2 minus. That does not happen. Okay, so make sure your formulas are correct as you're writing all these equations. So then on the right hand side you have the 2Na plus and 2Cl minus. Why do you have that? Because this is aqueous. The magnesium hydroxide is the solid here, okay, because this is where you determine whether something is going to be a precipitate or not, and it turns out that magnesium hydroxide is a solid. So once that's a solid, you're going to leave it as it is, okay, that's not going to be dissociated. Okay, so that's your ionic equation. So now for your net ionic equation, you go ahead and you cross out the spectator ions, right? So chloride here, and then sodium, and then the sodium here. Okay, so you do that. Oh, I have already done that. So let me go ahead and erase my thing here and let the computer do its thing, right? So sodium gone, and chloride gone. Okay, so once those spectator ions are gone, then you're left with your net ionic equation. That's it. That's how you write equations. Okay, so here is another one. I don't know if I want to go through it all again, okay, but it's the same kind of thing. Again, if you don't want to do this, it's okay. Just write the equation, do the double displacement. So here potassium will combine with chlorine to give KCl. Okay, so now if it is giving KCl, you still need to balance the equation, all right, because you have 3 potassium here and 2 chlorines here. So you do that later. First write the products, and actually that's really what I'm saying over here is you identify the K plus and the the cation and the anion. So you have the cation of one and the anion of another, and then you make the product. And you have the calcium of one and the phosphate of the other, and then you make the product. Okay, so that way you get that out. Now if you're comfortable with doing this, writing an equation straight away, that's fine too. Okay, but if you think you need some time and you need to practice this, so you go step by step. Okay, so write the cation of one and the anion of the other, form the product. Write the anion and the cation of the other, and then write the product. Okay, now once you have the products, the KCl, and the phosphate. Now you determine the solubility of both. Okay, so then you determine that phosphates are not soluble. So now you write your product. So you have KCl as a product and calcium phosphate as a product. So now you write the solid here for it. Then you can balance out the equation. Okay, so in balancing the equation, you make sure everything is taken care of. So balance the equation and then you write the ionic equation, which is dissociation. So here 2 times 3, so you have 6 potassium and you have 2 phosphates. So remember the 2 goes for the entire thing, and you already have 3 potassium ions there, so that's a total of 6 potassium ions, 2 phosphates, 3 calciums, and then 6 chloride ions. So make sure of your coefficients, okay? So don't miss your coefficients in there. So 6 potassium, 6 chloride, and calcium phosphate is insoluble. So you have that. That's the net ionic equation. How did we get the net ionic equation? Again, cross out the spectator ions, okay, on both sides. So potassium goes and then chloride is gone, and you're left with your net ionic equation. This is how we write equations, okay? So there's nothing much more to it. Okay, here is another one. So go ahead, decide whether the following reaction occurs or not. If it does, write the, again, same kind of question. So here again, we do the same thing, is we go ahead and write the cation and the anion of the other, so makes K2SO4 potassium sulfate, and then the bromine and the bromide and the magnesium of the other gives magnesium bromide. Oh, I need to fix these. There's always some fixing something, isn't it? Always. But anyhow, so here you get potassium sulfate and you get magnesium bromide. Now potassium salts are all soluble, and as far as halides are concerned, halides are soluble except for the heavy metals, right? So which means that everything is soluble. Okay, so which means that in this case, when you are looking at the products, because both of them are aqueous, it means that it's a big whopping nothing. Okay, so which means you mix 2 solutions together and you don't get any precipitate. Okay, so it's really no reaction. So be confident in that you're able to say that there is no reaction. Okay, because I can give you equations where there is no reaction. Watch it. Okay, so here is another one. So again, go through all of this again. Here I've given you the products, but you just have to figure out if they are soluble or not. So you can go ahead and look at the solubility rules, figure that out. So silver sulfate is not soluble, then you write these equations, and again, you will have to cross out the spectator ions, and then finally write the net ionic equation. Okay, so it just gives you a good practice again of how to dissociate. Okay, and that's an important thing, which is why I went over it in the previous section. So now let's talk a little bit about acids and bases, and yeah, this is a big portion of this chapter. I'm covering all the equations in one. Okay, so bear with me. So acids and bases are, 2 different kinds of chemicals. Acids are something that always will give protons, whereas the bases actually will give hydroxides. That's the old definition. The new definition is with the Bronsted-Lowry is that acids will give protons, whereas the Bronsted-Lowry base is going to accept a proton. Now what's a proton? It's just H+, okay, which means hydrogen without its electron. And remember, hydrogen has only 1 proton, 1 electron. So if the electron is gone, you only have a proton left. So it's called a proton. Okay, but it's actually H+. So you can call it H+, but everybody calls it proton. Acids are sour, bases are bitter. If you don't remember some of these properties, I'm okay with that, all right? But it's kind of nice to know. Acids are corrosive, whereas bases are caustic and they are slippery. Now, both of these give you burns, by the way, okay? So it's just a different kind of burn. They'll both burn you, okay? So be careful. And one of the best ways to get rid of acid or base on your body is just wash it with water, or anything else. Just wash it with water. Acids have a low pH and bases have a high pH. Now I'm going to learn more about pH values in Gen Chem 2, so not right now, but still it's low pH and high pH. And here are some examples, okay, for strong bases and strong acids. You already know about the acids because we've been talking about them. The only one that you know of weak acid was acetic acid, which I write like this, but you'll find it in books like this or on the internet if you look. So, you know, both of them are valid. And the other weak acid is HF, okay, which is hydrofluoric acid. Now you might think it's not, but it is, okay? So just kind of memorize that for now. Regarding the bases, the hydroxides, most of the hydroxides are strong bases, except for ammonium hydroxide, okay? That's a little bit of a weak base, and you probably remember it from our previous section that I wrote that in equilibrium, okay? And some of the organic bases, you're not going to encounter this in this chapter, okay? So we're going to work with weak bases and weak acids pretty much next semester. Okay, so just a little bit about acids and bases more is that you need an indicator in order to figure out if you have an acid or a base. So indicators are something that change colors with pH. Remember, pH goes from 1 to 14. So 7 is neutral. 7 is neutral. This is low pH is acidic, high pH is basic. So you can take a universal indicator, for example, and then your universal indicator will give you different colors, okay, with acids or bases. You're going to do some titrations in the lab, and then you see all of these colors, okay, in there. Regarding the acids, there is a monoprotic acid and a polyprotic. Mono means that it gives only one proton. Polyprotic means it gives more than one proton. So nothing too fancy about this. So again, here's the strong acids. And remember, I gave you this table before also. And what this shows you is how something is dissociating, okay? And strong acids will dissociate completely, which is what made them good electrolytes also. Okay, so here are the acid-base reactions. So acid-base reactions are also double displacement reactions. Just like precipitation reactions, they are also double displacement reaction. You will generally get salt and water as product, and some of the acid-base reactions give gases also. So I'm going to cover all of these, okay? Hopefully this will go a little bit faster because you already know how to write double displacement reactions. So here is your general reaction for neutralization. For all the acid-base reactions we are doing for us, there's going to be salt and water as the product, okay? So acid plus base gives you salt and water. So here is a very typical equation, HCl, sodium hydroxide. So hydrochloric acid and sodium hydroxide gives you, again, double displacement. So you can see the H is the red colors, they are all together. So that's the H of Cl. OH of the hydroxide gives you water. Okay, so now you can write it like this also if you want, right? HOH, because H is coming from acid and the OH is coming from the base. So you can write HOH also, but of course you're going to be chemists, so we'll write it as H2O. So note over here that water is a liquid. Okay, water is not aqueous. Water is already water. It's not dissociating, right? So if it was dissociating, it would be aqueous, but it's not dissociating. So it is a liquid. Everything else is aqueous because sodium chloride, is soluble in water. HCl is a strong acid, so it's dissociated, strong base dissociated, and this is soluble in water. And then writing ionic equation. So again, dissociate, dissociate, dissociate. But water does not dissociate because it is not an electrolyte, right? So it is not ionic in nature. It is not going to dissociate. So it comes out as a liquid. And then, of course, you go ahead and cross out your spectator ions. And then once you've crossed out the spectator ions, you're left with just the water. So H plus, OH minus, and then H2O. Okay, as your final net ionic equation. So you can see it's very similar to precipitation, except that now you just have a little bit of different chemicals that you're working with. Okay, acids and bases is what you're working with here. So here go the spectator ions. Okay, and you have your net ionic equation. So here is another example of writing a neutralization equation. So I did not give you the double displacement, um, the step-by-step thing. I'm just starting with the molecular equation there because hopefully now you don't have to go step by step. You're a little bit faster now. So identify the protons, okay, in the acid, identify the hydroxide in the base, and that's going to be your water. Now I wrote water here just so that you know that you can write salt and water or water and salt. It doesn't matter, okay? It's not like that it's a rule or anything, okay? So you just want to make sure you get both the products. So you get salt and water. So salt is here, water is here. Now this salt, potassium sulfate, is soluble in water because potassium is group 1 salt. So group 1 salts are all soluble in water. So that's aqueous. And then everything else is aqueous as well. Okay, so again, dissociate everything. Now H2SO4, remember, okay, how we dissociated. So H2 becomes 2H plus. Okay, over here, the 2 KOH is 2 for potassium also, and then 2 for hydroxide also. Okay, and then you write the products out, and then here is the net ionic equation after canceling out the spectator ions, okay, from there. So I hope you're getting more comfortable with writing these. You just want to make sure that you get the right structure of the compounds, okay, so which means you don't write potassium sulfate as KSO4. You have to write K2SO4 because you have to remember that sulfate is -2, okay. Again, that is the thing you need to memorize, okay. All right, let's go forward. And now here is another one, but this one is with gas. Okay, now usually I don't ask you to write equations with gases because they're a little bit harder for you at this point. Eventually it will become easier. Okay, so this one you just enjoy it in the sense that, this is what a reaction with gas would look like. So here is sodium sulfide with hydrochloric acid, and it gives us sodium chloride and H2S gas. H2S is hydrogen sulfide. When you mix sodium carbonate with hydrochloric acid, you end up getting carbon dioxide as a gas. Now, one of the things that you have probably done at some point or another is baking soda and vinegar to make maybe a volcano or something. And so that baking soda and vinegar gives us these products, which this acid that's formed, so I've highlighted that for you, the HCO3, which is hydrogen carbonate ion, and the proton from the acid gives us what's called carbonic acid. But carbonic acid is actually very weak acid, and it will dissociate to give water and carbon dioxide. So that's the gas that's coming out, and then water is formed as well. So usually like in carbonated beverages, you find carbonic acid a lot. Okay, so that's why it keeps giving you carbon dioxide in there. But anyhow, so these are some reactions that produce gas. So here is another one. You can go through it again. This is just for your information. I usually, as I said, if I give this to you, I give this like for you to identify the gas in it. Okay, and you should be able to identify the gas in there and maybe write a net ionic equation for it. Okay. So now we need to go into, oh, I have crossed out. Okay, so we are going to stop here for the two reactions for precipitation and acid base. We'll do redox in the next one, okay, because that's going to be pretty, not huge, but it's a little bit different, and also I want to take it separately. Okay, so this is it for precipitation and acid base.